turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast, the programme where we bring you the biggest breakthroughs and talk to the major movers and shakers in the worlds of science, technology and medicine with me, Chris Smith. And this week, we return to the world of fungi and why this is probably one of the most serious health threats that you haven't heard of.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
When we think of infections, viruses and bacteria usually spring to mind first, not fungi. But as we heard in our previous recent foray into the world of fungi, fungal infections caused 2 million deaths in 2020, and that was a year where much of the world was staying indoors and away from one another to fight off COVID-19. Indeed, viruses and bacteria have hogged the infection limelight for the majority of the time that microbiology has existed as a discipline. But this is changing, and multiple wake-up calls in the form of novel and emerging fungal threats causing human, animal and plant diseases, as well as a rising tide of resistance against our currently very limited repertoire of antifungal drugs, mean that scientists are now sounding the alarm. And, in partnership with the Wellcome Trust, in this follow-on episode on fungi, we're diving into what the threats are, why this is happening, and what needs to be done urgently to ward off the risk. To kick off, where are fungi making their presence felt? Welcome Senior Research Manager Sumi Robson.
They can cause everything from really mild, superficial infections. We've all heard of athlete's foot. But they can also cause much more severe infections, particularly when they become invasive. So if they get into your bloodstream and cause bloodstream infections. Candida, which causes thrush, if it's in your mouth or in the vaginal tract. But if it gets into your bloodstream, it causes a bloodstream infection, which can be really severe.
Why is it that they can have that range of being trivial right through to really severe? And is that changing?
Fungi, in a way, are opportunistic. Our body has a really good defense system. Our immune system is great. But when it's weakened in different ways, that's when fungi can really take a foothold. So weakened can be a bit run down. That's sometimes when we get fungal infections. But we really see it in patients with HIV and AIDS, people who are having chemotherapy or radiotherapy. But actually, increasingly, we're seeing it in people with more chronic conditions. So diabetes, chronic lung disease or liver disease, those sorts of conditions where their body's just a bit run down all the time and the fungi has the opportunity and takes a foothold.
Are we in good shape in terms of being able to treat it, though? I mean, if it was a bacterial infection, although we're worried about antimicrobial resistance, we still have quite a deep bench of drugs to fall back on. Can I say the same for fungal infection?
In a word, no. We only have 4 types of antifungal drugs which target different pathways within the fungus, and we're seeing increasing resistance to those as well. And probably most worrying is that we've seen a new pathogen emerge called Candida auris, which is what we call intrinsically resistant, or it was born resistant to a couple of the drugs, which means really we don't have much to fall back on at all.
Why is that? Why has there been a relative paucity of antifungals, but we have got loads of antimicrobials of other kinds?
I think 2 main reasons. Firstly, fungi are just overlooked and understudied across the board, right? So we just don't think that they just haven't been invested in the way we have in other pathogens. But also the real challenge with fungi is that they are so similar to us, which is great in some ways in that we can use them to study humans. But it means that if you find a drug that targets a fungus, it's quite likely that the protein or the molecule that it targets, we've got something really similar in us. So when we take those drugs, it causes side effects. And so finding a drug that kills the fungus without the side effects is really challenging.
Are there any areas of the world that we should particularly concentrate on that might be hotspots for this sort of thing happening? Because one of the things that we've seen time and time again with the emergence of disease is that these sorts of emerging infections do not need passports. They don't obey geographical barriers. They go where the people go. They go where the wind goes. So are there areas we need to keep an eye on, knowing that they might be the breeding ground and the origin, and then all of us are vulnerable?
I think it's generally where we find vulnerable populations, particularly vulnerable populations living close together, particularly in harder conditions. So I think humanitarian settings are somewhere we should really keep an eye on. But again, I think one of the challenges with fungi is that we don't really do any disease monitoring. So we don't know how much fungal infections are happening worldwide on a daily or annual basis. You know how we know every flu season, we know roughly what flu strains we're likely to see. And with COVID, we were all very familiar with constant disease tracking. But that doesn't happen at all for fungi. So we don't really know what fungal pathogens might be happening.
And is that something you think needs to change? Is that something, for instance, a funder, like the Wellcome Trust even, should be saying, this is what we need? We need some kind of map supported by genetic codes and so on, so we can keep tabs on who's got what and where.
Absolutely. I think especially for those pathogens that we think, fungal pathogens that we think are on the rise, we really need to be keeping a closer eye on them and linking it really closely to climate data so that we can see as fungi are adapting to climate change and as the climate is changing, are we seeing changes? Are we seeing differences? And where are those differences happening? Which populations are they affecting more so that we can then, go in with suitable interventions?
Sumi Robson at The Wellcome. And as Sumi outlined, when it comes to combating disease risk, a good place to start is by asking who is most vulnerable and where do they live? Because in this modern world, where there are about 1.5 million people airborne around the planet at any moment in time, and with no major city more than 24 hours from any other, infections can move very fast and in significant numbers. They go where people go, of course. And we're seeing a very significant and increasing flux of people from poorer parts of the world moving towards richer economies as those latter countries seek to tap into sources of cheaper labour and skills. But it's in those poorer places where people are migrating from and where underlying diseases that drive the emergence of novel fungal infections are common that human conflict with nature is intensifying, and with it the risk of fungal disease emergence. These are also often the places where climate change is likely to intensify all of these problems. This is very much in the purview of Nilesh Govender, an epidemiologist at Wits University in Johannesburg.
Low and middle income countries are particularly vulnerable to fungal diseases. I work in South Africa, and we have a large population at risk for infections that are both life-threatening or disabling. We've got the largest population living with HIV worldwide, and these people are at risk of deadly fungal infections such as cryptococcal meningitis or pneumocystis pneumonia. And people with TB are at risk for superadded fungal infections such as aspergillosis. In hospitals in low and middle income countries, these hospitals often have higher than expected bed occupancy, so they're overcrowded. They've also got limited resources for infection prevention, and this can set the scene for large disease outbreaks, especially among very vulnerable populations, for example, sick, small newborns who have to stay in hospital for weeks to months.
From all of those risk factors you've outlined, it sounds like this is a problem that's a clinical iceberg. It's probably much bigger than we already document. And B, it's likely to get worse because all of the pressures you've just summarised are intensifying.
I think that's absolutely true. Low and middle income countries just don't have the capacity to respond to fungal disease epidemics. We have a lack of diagnostic tests, which affects our ability to identify cases of fungal disease. This really delays life-saving treatments, and many people will then die unnecessarily. This also reduces our ability to track or monitor fungal infection outbreaks. We also have a lack of access to antifungal medicines, which means that even when we do recognize fungal diseases, they're not treated and people suffer or die as a consequence. And also when antifungal medicines are available, we often see weak stewardship. So these medicines are being used inappropriately for the wrong indication, at the wrong dose, for the wrong duration.
Some people often say that because many of these problems are not a first world problem, rich countries are less affected. They don't tend to register very high up the priority pecking order for funding and research in those places. But they nevertheless should be reminded that what starts in poorer places often makes its way to richer places. And I suppose we've seen that with diseases like COVID and with HIV. So is this one of the same? Is it that we can't afford to take our eye off fungal infections because as the problem intensifies, it could well spill over and will become a priority everywhere?
We currently see hundreds, thousands of cases of cryptococcal meningitis, mostly among people living with HIV. It's caused by a fungus called Cryptococcus. It's listed as a critical pathogen by the World Health Organization. We've got evidence that this fungus may have actually emerged in Africa to become a pathogen, principally by its ability to grow at human body temperature. But we actually believe that there's an extraordinary variety of non-pathogenic cryptococcal fungi in the African environment associated with soil, beetles, small mammals, and potentially as the climate changes in Africa, we're concerned that some of these non-pathogenic fungi could also gain virulence traits to cause human infections, and these human infections may affect, people across the world, not just in low and middle income countries. So I think there's a shared global threat from fungi, and so we really do need to take this threat very seriously.
Do you know what's really surprising to me is that no one's talking about this. I know you and I are, and we're trying to raise awareness in this programme, but most people are unfamiliar with what is happening. Is the fungal threat creeping up on us in the same way that sort of antibiotic resistance has, and to a certain extent other pandemics like obesity? We've sort of walked into this situation.
Well, we tried really hard for that not to happen. So in 2022, I was involved in an expert group with the World Health Organization. We developed a fungal priority pathogen list, which flagged 19 fungi which affect human health. And we're actually currently working on a blueprint for action to address fungal diseases globally. And one of the key action items, of course, is awareness and education. This podcast, I think, will go a long way to raising the profile of fungal diseases. But of course, we also need to think more broadly. We need to build capacity to facilitate diagnosis of fungal diseases. We need better surveillance to understand the burden of fungal diseases. We need to track fungal antimicrobial resistance. We need to monitor outbreaks and emerging threats. We need antifungal stewardship. We've got a really limited antifungal armamentarium. There really are very few antifungals available. And so we also need research and development for new medicines, new diagnostics, new technologies.
Nilesh Govender at the University of the Witwatersrand in Johannesburg. With Nilesh's list of urgent actions in mind, we now turn to the cutting edge of research focused on fungal diseases. And as we've heard earlier in the programme, we currently have only a very limited repertoire of drugs with which to combat fungal infections. This is partly because fungal cells are so similar to our own, so it's harder to identify differences between the two that drugs can exploit. But that's the goal now, to better understand the mechanisms by which these organisms invade the body. This will help to highlight potential targets for novel drug development. It's what Carolina Coelho is doing at the University of Exeter.
If we understand how they get into our bodies, if we identify certain molecules, which are kind of the chemical points of entry, we can try to block them. We can try to decrease them with drugs. We can try to create vaccines. Fungi are really interesting because they're really masterminds of chemical manipulation. If we understand better these chemical manipulations that they do to our bodies, we can fight the disease. But the other interesting thing is that Every time we understand better these chemicals that the fungi produce, a lot of times we have alternative uses for it. So a lot of these chemicals that the fungi produce are, for example, used in modern medicine. Things like penicillin, cyclosporin, and the drugs that lower the cholesterol that many people in the world, millions of people worldwide are taking, the statins, are all derived from the chemicals that the fungi produce naturally and that we were able to hijack for our medicine.
How do they actually get in, though? Because that's the crucial question. How do we actually track down the route into the body that these sorts of organisms take?
Mostly we know where they are present in the environment, at least the ones that cause important diseases. We know, for example, cryptococci exists in the environment. And we have clues from many different systems. So, for example, we know that koalas tend to have nose infections with cryptococci, and we know cryptococci is on the leaves, so then we kind of identify the anatomical place of entry. So we think it's inhalation. For example, for Candida, we know that it exists within the skin of most of our bodies, and it also exists in our guts, right? So actually, Candida already exists in our bodies. Now, what happens is, due to some change, usually when the host, the human, is a little bit less healthy, then it creates an imbalance in the system and they can start really to create havoc. So, for example, Candida will start leaving the gut and getting from the gut into the bloodstream. And Candida should only be in the gut. In any other organ, like the heart or the bloodstream, it will really create a huge amount of problems.
If we look at the fungus, if we look at, say, a candidal cell, when it's being pathological compared to when it's just sitting, we say harmlessly, but living in our guts harmlessly, living in our skin, in check, kept in control, does it look different?
Yes, absolutely. So the Candida in our gut tends to be round. It looks like an egg. We kind of describe it as an egg. But again, once that imbalance is achieved, it can make what we call a hypha. And a hypha is a tube. And this tube is so strong that it can literally pierce through our tissues. And it's much more harder to treat because then it becomes of a size that is larger than our immune cells. If you're trying to fight an enemy that's bigger than you physically, that also becomes difficult. So then you need a different amount of weapons in our immune system. And with Aspergillus, which is also associated with serious infections, but it's also a trigger for asthma. When we grow it in the lab, and you've all seen Aspergillus growing on oranges. But for example, when we grow it in the lab, we have to seal everything we grow it in because it can lift the lid out of certain plastics, and it just lifts the lid because the fungal growing is actually that strong.
If we can therefore see that the thing puts itself almost into an aggressive mode, it's sort of the fungus with a dog with its lips drawn back and its teeth bared, that's the kind of active form. If we can work out how it's doing that, that presumably discloses a vulnerability. So that's our way to then say, aha, that's how we attack this. So we can detect when it's in that form and attack it when it's vulnerable. And then then we've got a way of stopping this.
Absolutely. And that's precisely what the center is trying to do and all the other medical mycologists. So, for example, if we can block a certain chemical from being produced, if we can make a vaccine that then binds to that chemical and blocks that chemical, absolutely. And that's something that we're really, really trying to work out. We could try to develop drugs to block it. And again, sometimes that chemical is useful in other contexts because what it does during the fungal disease, it could be useful in a different context, right? So for example, from the beginning, cryptococci are coated in this sugar capsule that makes it invisible to the immune system. So once we know the structure, we create a vaccine that can target it.
Carolina Coelho there at the University of Exeter.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, Perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Today, fungi are back under our microscopes as we recognise the growing threat they pose to environmental, human and animal health and try to find new ways to control them. Speaking of which, for close to half a century, we've relied on fungicides, fungus-killing chemicals, to keep our plant crops healthy and our population fed. But because the molecules that farmers use are the same or extremely similar to the ones that we use in hospitals to treat fungal infections, the high rates of consumption in the environment of these chemicals is driving the inexorable evolution of fungal resistance, with obvious human health consequences. Here's Matt Fisher at Imperial College London.
The worst fungal infection on the planet is caused by the very common mold Aspergillus fumigatus. It causes half the global burden of fungal disease. Over 2 million cases per year. It kills more humans than malaria or tuberculosis. Now, the problem there is it's everywhere in the environment, and that's where we get exposed to it. It forms mold spores, it's a bioaerosol, but it's also exposed to those fungicides that the farmers use. So what we've seen is that Aspergillus has evolved resistance to the same clinical drugs that are used by doctors, because those are the same drugs that the farmers are using. This is called dual use.
Then the Aspergillus that's floating around in the air, because if you see a mouldy patch on the ceiling, that probably is Aspergillus in that mouldy patch on the ceiling where you've had a leak or something, isn't it? So are you saying then that the spores that's producing that I could be breathing in could well have resistance now?
Absolutely. So we asked this question: of those spores of Aspergillus, which are soft, blown on the breeze, what proportion of them have become resistant to frontline clinical antifungals? Those are called the azoles. And the azoles are also the same fungicides that the farmers are spraying. So we had a wonderful PhD student, Jen Shelton, and she got a cohort of citizen scientists to catch those fungal spores using little sticky samplers, which then were returned in envelopes to our lab, and then we cultured the mold and then calculated the proportion that was resistance. And the incredible number that Shing came up with was that 1 in 20 of the spores in the air are now resistant to multiple azole antifungals.
1 in 25%. That's huge.
Yes, and it wasn't just a single time shot. She repeated this experiment 4 times across 2 years, and the number that she got was always the same.
If I wind the clock back before the time we had these drugs, though, would I still find that resistance? Because some microbes just happen by chance to be resistant to things, and when we've enriched that resistance by using the drug. So if you go back in history, do you still see this resistance and we've just made it more common, or did it not exist at all?
1980 was when the azoles were invented as fungicides in the environment. That's when we started seeing the resistance markers in the genome. And since then, there's been a steady explosion of resistance to this 1 in 20 spores number that we find now.
What can we do about this then? It sounds like we've created, through human overpopulation and human movement, of not just us, but animals and plants, we've created enormous opportunity. When we then add drugs onto that, even greater opportunity for the emergence of these sorts of resistant forms. What can we do about it?
The first thing to bear in mind here is we have to feed the world. And to do that, we have to ensure we had food security. Now, those fungicides are wonderful drugs because they mean we can grow enormous amounts of crops. Everyone gets fed. However, we have this problem of resistance. Now, if you're a patient with azole-resistant invasive aspergillosis, you will die unless you're given a new therapy. And thankfully, we have invented those new drugs. There's 2 that are coming out of phase 3 clinical trials. And those are the hope for those patients that they will be able to, if they do have a resistant infection, they'll be able to be moved onto this new therapy and the resistance problem won't present itself.
But won't we be back to square one? Presumably if farmers and so on, all the mechanisms you've outlined that have driven the emergence of resistance, if they get hold of those drugs and start using them on their farms, are we not just going to be back to square one? We'll get resistance to those agents and then we'll have nothing.
You're right. If you find a new drug target that works against fungi, it's not going to just be used in the clinical space, it will also be used in agriculture. And this exact scenario has presented itself. So the newest kid on the block, the new mode of action antifungal, is called Olorofim. And it's an absolute wonder drug. It treats invasive aspergillosis brilliantly. However, it's now being used in the environment with an environmental analog called iflufenoquin. And this has been registered as a fungicide in the United States. So you're right, the opportunity here is to spin the roulette wheel of resistance another turn as this new mode of action antifungal starts to become increasingly widely used as an environmental fungicide.
And what do the regulators say? Will they wave that through?
This current drug is being scrutinised by the European Union, and the question of whether it will evolve resistance to Olorofim is being asked. And if they decide that the risk exists, then they may ban the use of that chemical in the European Union. And we're months away from this decision, so literally we're on tenterhooks to see which way the European Union jumps on this one.
That's just one jurisdiction, though. And these sorts of microbes don't observe geography. They're not interested in borders. They go where the people go. And so if other places are using this stuff with abandon, resistance brewed up there will easily end up here.
What may happen is that the European Union will make a decision. That's a very large and authoritative body. It's hoped that that decision will be followed by other countries, that they'll see sense that there are great fungicides for use in the environment, but certain modes of action should either be ring-fenced for human use or used very intelligently in a risk-based manner in the environment. The problem of resistance is often a slow-moving one, so this isn't something that needs to be done in a hurry, but azole resistant took 20 years to emerge. We have some time here, but we need to get it right.
One to watch. Matt Fisher there from Imperial College London. As Sumi Robson said at the very start of this programme, our ability to treat fungal diseases is a long way behind the curve for that of bacteria or even viruses. So what challenges do the medical mycologists charged with creating the treatments of the future face? I've been catching up with the University of Exeter's Neil Gow.
There are drugs which are developed against the cell wall. This is a sort of structure which encapsulates the fungus. And bacteria have cell walls, fungi have different cell walls, but humans do not have cell walls. And this is an excellent target because virtually everything in the cell wall of a fungus is not found in human bodies at all. So there's great opportunities to develop new drugs, and echinocandins are an existing class of drugs which target the biosynthesis of a critical component of the cell wall, beta-glucan, and these are on the market. There's several versions of the echinocandins which are available for clinicians to use to treat fungal infections.
Does it matter then what sort of fungus we're talking about, whether it's one that preys on crops or one that might attack a person or an animal? Because they share those similarities, are they likely to be amenable to the same sorts of treatments?
Well, you're absolutely right. The differences between the fungi which cause human infections and those found in the environment, and even those which cause plant infections, are rather slight. And that means that the agents which can be used to treat fungal infections, often there can also be used to treat plant infections. Now, this actually in itself is an issue and a problem, because we now know that azole resistance is a problem which you see in organisms which cause plant disease. But some of those organisms are also organisms which can cause human disease. And therefore, you can get an azole-resistant fungus in the environment, and the spores spread very widely in the air. They even get into hospital settings. They certainly get into patients who have got sensitivities or immune deficiencies, which make them vulnerable to fungal infections. So they can be pre-colonized or infected by a fungal strain which is already azole-resistant. And that's a major issue for us. So these are the sort of dual-use antifungals, one's use in the clinic and one use by agricultural practice to treat crops. And the only two new classes of antifungals which are in development, one's called fosmanogepix and one's called Olorofim. These are very exciting new drugs to treat fungal infections clinically. But there are very similar compounds in the same class of agents which are also being trialed in field to treat diseases of plants. And of course, there we are concerned that maybe we'll see resistance emerging environmentally, which can be transferred again into a clinical setting.
Are we also creating new opportunities for the fungal world to effectively invade us or exploit us? For instance, by immunosuppressing people who have cancers or certain things like organ transplants, or at the same time giving people big doses of antibiotic drugs to treat bacterial infections, and in the process almost clearing the way for fungi to take over. So are we creating opportunities and creating diseases that didn't exist historically through modern medical practices?
That's actually a major point in why fungal infections are now becoming much more prevalent. In the past, many people used to succumb to diseases like cancer, but now improvements in their treatment has meant that we can look after, maintain, and people will survive their cancers. But often the treatment makes them very vulnerable. For example, they might be given a regimen of drugs which reduces their natural immunity. And during that period of vulnerability, cancer patients are exquisitely in danger for being colonized and being infected by a fungus. And in fact, many cancer patients spend many thousands of pounds simply providing antifungals to prevent that possibility. And yet most people are very unaware of the threats imposed by fungal infections. So it's come through the ranks and become a major part of the global health protection efforts.
Do you think then that people are not paying sufficient heed to this? Is this not getting enough attention in your view?
This program is one bit of evidence that people are beginning to understand that this is a problem that needs to be addressed. And the funders, such as the Wellcome Trust and MRC and other funders of research across the world, are also upscaling their attention to fungal infections, which is very welcome indeed. One issue that remains, though, is because this has been a burgeoning problem which has expanded considerably in the last 20, 30, 40 years, the population size of researchers who work in medical mycology remains very small. We've not yet caught up with the demand that this topic really requires. And indeed, infectious disease budgets in most parts of the world, about only 2 to 3% of those budgets which are allocated to infectious disease go to medical mycology. Not because this is not important, not because the funders don't want to fund it, because there are relatively few medical mycologists like myself putting in grants. But what we need is more people on the ground tackling this area.
So what does the future look like from your perspective then, in the near term and also the long term? Are you worried?
So we are concerned that there are new epidemics emerging, and we need to have a response in place to be able to deal with those. I'm also optimistic that the quality of research in this area has been very high, and we are seeing new drug classes being approved. There's 4 new drugs which have been authorized in the last 10 years, but there are also several which are in clinical development in various stages of being tested, which should help our position. But we remain blind in a number of ways. So, for example, as a virologist, I'm sure you'll be appalled to remember that in medical mycology, we don't have a single vaccine, not one vaccine available. Not that we couldn't develop them, but there hasn't been sufficient work to be able to get them on the ground. And we still need diagnostics which can make sure that doctors can quickly realize they've got a fungal infection and not a bacterial or a viral infection. And we also need to know a lot more about the immunology of fungal infections so we can develop immunotherapies which can support us. A lot of work in that background, but it'll be a while before it emerges into the clinic for a day-to-day use.
Thought-provoking stuff. Neil Gow there from the University of Exeter. So the call to arms is there for those within the field of medical mycology. Far more research and resources are required to effectively stem the tide of resistant fungal diseases. And as Matt Fisher said, we have the time, but we do have to get it right. If you'd like to go back and review our first episode on fungi, you can get that at nakedscientist.com/podcasts. But this time next week, we're going to be off to Trinity College, Cambridge, to hear from Simon Baron-Cohen, the leading light in the field of autism and Asperger's research. He's our next titan of science. We will, of course, bring you the latest science news breakthroughs on Friday. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the Naked Scientist team, thank you for listening, and until next time, goodbye.